Good morning. I'm Kate Tolstaya, and today I'm defending my doctoral thesis titled Scalable Learning and Distributed Robot Teams. Mobile robots are already in use for mapping, agriculture, entertainment, and the delivery of goods and people. As robotic systems become more affordable, large numbers of mobile robots may be deployed to accomplish tasks faster and more efficiently. The robots in this demo from my advisor's lab are coordinated to play the James Bond theme on a variety of musical instruments. But what's not pictured in the video is the centralized computer that is required to localize the robots and to send commands to the robots at a high frequency. As the complexity of missions are scaled up, the deployment of tens or hundreds of robots may be required. And as team sizes increase, the centralized architecture may become impractical. This flock of birds is decentralized. Each bird observes those around it to decide the motion of its wings. This talk focuses on the three main algorithmic obstacles to the scalability of robot teams: coordination, control, and communication. Our goal is to implement decentralized architectures in which each robot can operate autonomously, but still cooperate across the team by using local information and communication with others. The most important tool that allows us to develop scalable architectures is the ability to represent a team of robots as a graph. We represent each robot in the team as a node in the graph, and the edges indicate different relationships that robots can have with each other and with the surrounding world. The graph may have different types of nodes, such as robots or even physical locations, and several different types of edges between them. First, robots in the team may be able to communicate, which we represent using edges between robot nodes. Secondly, robots may be able to sense the surrounding world, and so we add edges from robots to objects. Finally, mobile robots will also need to move to accomplish their mission. If the robot has a discrete set of possible actions, these can be represented as edges from the robot to a location. In this talk, I'll cover our approaches to the three main algorithmic challenges to scaling up robot teams. First, I'll focus on coordination of a robot team for the task of coverage in a known map. The main emphasis here is on high-level coordination, or how robots can use local information to divide up the subtasks of the team's mission. Next, I'll discuss the problem of flocking, in which we focus on low-level control of robots that must align velocities and avoid collisions. Finally, I'll talk about the problem of data distribution and how we can address it by allowing robots to decide the topology of their wireless network to minimize the latency of the information distributed among all agents. Given a graph representation of a robot team, we can now use graph neural networks to process the information within the team in a scalable way. So let's jump into some graph neural network fundamentals. While there are a lot of different formulations of graph neural networks, today we'll follow the notation from DeepMind's GraphNets framework that is one of the more general and comprehensive formulations. We define a graph signal by its edge and node features. If the nodes in our graph are robots, the node features may be the robot's positions or states. The number of features across all nodes is typically fixed. The directed edges in the graph are represented using a tuple: the features for the edge, the index of the receiver node, and then the index of the sender node. An edge may be, for example, an edge feature may be, for example, the distance between two robots. One thing to note that this is actually a simplification of DeepMind's framework. We've removed the ability to provide a set of global features, so you should refer to their archive paper for more detail about the full formulation. So now we have a graph that represents our problem. How do we build a neural network that can process it? First, let's think about a convolutional neural network that would be used for images. An image is really one particular case of a graph. It's a graph with all of the pixels connected by a grid. So a CNN uses filters that slide across the image and apply a function to each patch of nearby pixels. The graph analog of a CNN is a graph filter, that can operate on nodes that are connected by edges. A graph filter could, for example, take the average of each node's one-hop immediate neighbors. And we can compare this to a convolutional filter of width 3. Now, let's formalize the graph filter in the notation and language of DeepMind's framework. This framework is built around the graph network block that applies the same 3 operations to every node and edge in the graph. The first operation is the per edge update. For each node, this operation takes as an input the features of the edge and its sender and receiver node features, and then it outputs the updated edge features. The next operation is an aggregation of the features for all of the edges going into each node. Last is the per node update that takes as an input the node's features and the aggregated edge features, and then it outputs the updated node features. The node and edge updates are typically parameterized as neural networks or sometimes as identity functions. The aggregation operation can be a max, sum, or a mean. In this work, we use an average over edge features as the aggregation function because it generalizes better to variable numbers of edges per node. But the important characteristic of this function is that it eliminates the ordering of these edges. And this property is called permutation invariance. Each graph network block now contains several learnable functions that can update the node and edge features for a given graph signal. We can stack these GN blocks to build a deeper architecture that can capture broader patterns throughout the graph, like we could stack convolutional layers. The architecture pictured here could be compared to a 3-layer convolutional network with filter widths of 3 and a stride of 1. These layers may share weights or they may have distinct weights. And the number of GN layers is a key hyperparameter that determines how far information can propagate across nodes in the graph. Now, let's see how this stack of graph network blocks can fit into a broader architecture. Pictured here is the architecture that we've used in the 3 projects I'll present today. This architecture is novel, and we've developed it for this work, combining the key parts of the aggregation GNN from Alejandro and Fernando's work and the encode process decode architecture from DeepMind. The encoder, decoder, and output transform operations are local, operating on the feature vector for each node and edge separately. The core blocks of the architecture are GN blocks, like we just discussed, and they actually share weights. The repeated application of these operations can propagate information further and further within the graph. Sharing weights means that we have fewer learnable parameters, so this model may be faster and easier to train. And after the core graph network operations are applied, we concatenate the outputs from the local 1-hop, 2-hop neighborhoods, and so on. And this concatenation is a contribution of our work and allows the model to weigh more distant information differently than local information. And for the output transform, we typically use a linear layer. So this is just one example of a graph neural network that has been extremely effective in my work, but in the literature, there are countless other examples of architectures that may work better for other applications. To train these architectures for multi-robot control, we typically use centralized training. And by that, I mean that all of the observations from all robots are accumulated and synchronized when they are used as inputs to the model during training. If we want to use imitation learning, then we can obtain a centralized expert solution and then use a supervised loss to train each agent's policy to imitate the expert. On the other hand, if there's no expert solution for the task, but we can describe the objective concisely using a reward function, then we can use reinforcement learning. Since the team is fully cooperative, we use a single reward for the whole team, essentially treating the team problem as a single agent problem. Because we have one reward signal, we use a centralized value function that's parametrized as a GNN in this work. Despite training in a centralized way, The architecture of the policy enforces the use of only the local information available to each robot, which means that we can deploy the team's policy in a distributed way. The GNN architecture scales well to much larger teams during execution, so we can train with a smaller centralized team and then deploy the distributed controller to a bigger team. The centralized training approach improves the training speed and also allows us to use off-the-shelf single-agent RL algorithms so that we don't need to worry about multi-agent challenges like non-stationarity. One downside, though, is that there are tasks that do fundamentally change as you add more agents. In this case, we may need to think about distributed learning algorithms that would allow agents to train local controllers and then combine their experiences. This topic is beyond the scope of this talk, but there's some related work in my dissertation. Now that we've covered the fundamentals of graph neural networks, let's look at a few applications. The first application I'll talk about is coverage, which highlights the need for robots to coordinate their actions. This work was a collaboration with James Paulos, Vijay Kumar, and Alejandro Ribeiro. The task of coverage is to navigate a team of robots to visit points of interest on a given map. This kind of approach could be applied to mapping or surveillance. Our first step in solving this problem is to discretize the map into a grid of locations. This simplification allows us to formulate the coverage task as a vehicle routing problem, for which optimization-based solutions are widely available. The problem is that the optimal solvers require exponentially more time for larger maps and larger teams. So our next step is to collect a data set of moderate-sized graphs for which optimal solutions can be obtained within a few seconds. And we use this data set for imitation learning to obtain a controller that can then generalize to larger maps and teams. To apply graph neural networks to this problem, we require a graph representation of the task. We discretize the map into a set of waypoints, or locations in space, which become nodes in the graph. And graph edges indicate that robots can move between adjacent waypoints. The graph represents the current state of the mission and also acts as a computational tool that will allow our solution to generalize to new maps and teams of different sizes. Now, we want a controller that will output the next waypoint for each robot. We parameterize this controller as an aggregation GNN described in the first section of this talk. By repeatedly applying the graph network operations, each robot can obtain information about points of interest and locations of other robots, allowing them to coordinate locally to maximize the number of points of interest visited and the time limit. The learned policy outputs a scalar for each edge adjacent to a robot, which determines the probability that the robot will travel along that edge to the next waypoint. We summarize the architecture in this one-line equation. The number of GN operations is a hyperparameter that we're about to explore in more detail. The number of GN operations is also called the receptive field of the GNN. The receptive field is the distance in the number of edges that information can traverse during a single inference step of the model. I've pictured an example scenario in which the robot in the center is using a GNN with a receptive field of 10, so it can process the information about the locations of about 2 of the other robots, and also the points of interest within this region, marked in orange. If we removed any part of the map outside of the 10 hops, the GNN policy would still compute the exact same action for this robot. This fixed size receptive field enforces the locality of the controller. Robots can make good decisions that approximate the optimal expert without having access to or having to process the entire map. One aspect of our architecture that makes this approach scale well to larger teams and maps is the sparsity of the waypoint graph. By design, each waypoint is connected to at most 4 other waypoints, and the GraphNets library leverages this by implementing the graph updates using sparse operations. So the memory requirements of this GNN scale linearly with the map size and team size. Other applications of GNNs to routing have used dense GNNs, which require the computation of distances among all nodes in the graph which can quickly become impractical in maps of thousands of nodes. Other approaches use hierarchical aggregations in which clustering is used to propagate information between distant nodes in the graph. But the problem is that we can't apply this approach to closed loop control in graphs that are changing over time, since the clustering procedure may be too expensive to perform online. And the sparse graph approach is the most practical tool for closed loop control of robot teams. We measure the performance of our controller in the average number of points of interest visited by the team over 100 episodes. To provide a fair comparison to our local GNN, we developed two baselines that have access to only local information. The greedy controller routes each robot to the closest point of interest in a radius of k hops, equal to the receptive field of the GNN. And we also have an expert controller that is an optimal receding horizon controller. And in other words, it plans for trajectories of k steps and then executes the first step, and then it replans. We observed that GNNs with receptive fields of 13 to 19 outperform the greedy baseline. The performance of the GNN slowly saturates when we increase the receptive field up to 19. But of course, the optimization-based approach outperforms our learner, but it requires 2 orders of magnitude more computation time per episode than the GNN. We can now make the problem more challenging by hiding unexplored portions of the map from the team. This approach could be used for exploration or mapping when the map is unknown at the start of the mission. During training, we generate centralized omniscient solutions for the trajectories of the whole team. Then we train the policy to imitate this expert using only local information about the partial map. In this task, we've added an extra node feature that indicates the frontiers that are adjacent to unexplored regions. The agents can now learn to reason about the trade-offs of pursuing known points of interest versus frontiers. The nonlinear GNN outperforms all baselines since the baselines don't weigh frontier nodes greater than points of interest. While a heuristic could be designed to make this trade-off, machine learning is basically the principled design of heuristics. The GNN controller was trained on teams of 4 agents and maps of about 200 waypoints on average. Then we're able to test the zero-shot generalization of this approach to teams of up to 100 and maps of over 5,000 waypoints. Problems of this size are completely intractable for the VRP solver, so we're unable to benchmark the performance of this expert baseline, but we're able to see that our GNN controller exceeds the performance of the greedy approach. The final experiment in this project was the application of the GNN to a simulation of 10 robots traversing a city. The robots marked in green must visit the points of interest marked in red. The GNN was able to coordinate this team of robots to visit hundreds of points of interest safely and efficiently. This work was a demonstration of the high-level coordination of a robot team, but there are 2 shortcomings that I'll address in the next 2 sections of the talk. First, we assume that the full state of the team and map was available to all agents with no latency or communication delays. And we also assumed that a controller was provided that moved the robots to the next waypoint, and also that the robots had a collision avoidance strategy. In the next section of the talk, I'll focus on the problem of flocking, in which robots must avoid collisions and align velocities based only on local observations of neighbors. This work was a collaboration with Fernando Gama, James Paulos, Vijay Kumar, and Alejandro Ribeiro. In flocking, Our goal is to get the robots to agree on velocities and regulate inter-robot spacing to avoid collisions. We assume that each robot can observe neighbors in a given radius to compute the relative positions and velocities. The existing bio-inspired approach uses a potential function to control agent spacing. This potential function pushes robots apart if they're too close together and pulls them in if they're too far apart. The controller also uses a consensus rule to align robots' velocities. When the observation range is too short, close to the desired inter-robot distances, the pre-designed controller often fails. We focus on regimes in which a completely localized controller fails, but a GNN that leverages communication between agents enables the team to align velocities and regulate spacing. So first, let's identify the graph structure that will allow us to apply graph neural networks to this control problem. For this task, the nodes in the graph are agents, and the edges connect robots that are within range. We assume that robots within range can not only observe each other, but can also transmit messages. The edges represent both the perception and communication capabilities of the robots. In order to more accurately simulate wireless communications, we consider each transmission to incur a time delay of 1 unit. Now, we can build on this communication capability further. Rather than simply transmitting a robot's local state, each robot can also retransmit information that it has received from others. The use of multi-hop communication for consensus is a novelty of this work. The challenge, though, is that each communication link incurs a time delay. So the information that has been retransmitted once will incur a time delay of 2. The further the information travels, the more delayed it will be. And it's unclear how the controller should weigh up-to-date local information as compared to more delayed and distant information. So we train our controller to imitate a global expert that assumes that all agents are connected. The controller outputs a 2D acceleration for each robot. A challenge in formalizing this architecture in the GraphNet's framework is that the connectivity of the graph varies with time as agents move. So we need to define graph updates that respect the current connectivity of the team. We implemented this architecture from scratch in PyTorch without relying on the GraphNet's library, because we needed to perform graph convolutions that track the corresponding network connectivity and system state for each layer of graph filters. We measure the performance of the flocking controllers by the variance in agents' velocities averaged over the episode. We compare the GNN with receptive fields of 1 to 4 against 2 baselines. The local controller uses only the observations of neighbors within range, providing the worst-case bound on performance. The global controller also assumes that all agents are connected, so it acts as a best case. We see a clear improvement in the performance from a receptive field of 1 to a receptive field of 3. The improvement is especially significant when agents have a limited communication radius compared to the ideal interagent distance of 1. The improvement starts to saturate from receptive fields of 3 to 4. We hypothesize that this is because information delayed by 4 or more time steps becomes less useful. The increased receptive field is also more useful as agents are initialized with larger velocities. The consideration of time delays in the system becomes more relevant as agents move further and further with every time step. We also test this approach on 50 drones in the AirSim simulator, which simulates complex dynamics and stochastic delays. Using 3-hop or 4-hop GNNs helps us achieve the desired formation with minimal cost. Notice that the centralized controller gives us a best case bound, while the local controller provides a worst case bound. In our simulation, we observed that the baseline local controller fails dramatically and the flock separates into subflocks. This controller observes only the relative distance to neighbors and their differences in velocities. The GNN uses the same set of observations, augmented with delayed communications with neighbors. If we use a 4-hop GNN, then the agents can quickly make the desired formation. In our work on flocking, we assumed that a deterministic communication model in which agents within a given radius can always communicate and always incur the same latency. In real wireless systems, this assumption is very impractical, especially in the presence of wireless interference. In our final section of the talk, we develop a framework for data distribution among a team of robots over a wireless ad hoc network. This work was a collaboration with Landon Butler, Daniel Mox, James Paulos, Vijay Kumar, and Alejandro Ribeiro. Most multi-robot control algorithms assume that each robot has access to low latency information about the states of other robots. In our coverage project, we assume that each robot had ideal knowledge of the full state of the entire team. This assumption is often unrealistic, especially for mobile teams or wireless communications. The robots may be deployed in an environment where full connectivity within the team is unavailable, and their communication channel may be subject to interference. The robots may also move large distances during the mission, or maybe they have no a priori information about the starting locations of other team members. The combination of these factors makes it especially challenging to establish an ad hoc network to distribute the required information with low latency. For mobile mesh networks, existing approaches typically use flooding, in which agents continually broadcast the same packet until everybody has obtained it. This can be extremely inefficient and cause a broadcast storm. Other solutions use heuristics to reduce network overhead and minimize the age of information. Combining the most powerful aspects of the existing approaches, we've designed a new protocol for simultaneous data distribution and route discovery. This protocol is slotted, so that means agents may transmit simultaneously. And at the beginning of each time slot, each agent chooses not to transmit or selects one recipient. The agent then transmits its full knowledge of the system state to the recipient, subject to interference from others' transmissions. If the recipient has successfully received the packet, it will send a response back to the sender, also containing its full data structure. One reason that we include a response phase is to align agents' incentives. With each successful transmission, an agent helps the rest of the team while obtaining newer data for itself. The main problem with this peer-to-peer approach is interference. Especially at the beginning of training, transmitted packets are lost most of the time. Inspired by broadcast-style flooding algorithms for route discovery, we allow agents to intercept transmissions that are directed to others. The successful receipt of these packets we call eavesdropping. In our problem, eavesdropping is especially helpful at the initial phases of the route discovery process, when agents have no information about the rest of the team and make decisions completely at random. With eavesdropping, transmissions may fail to reach the intended recipients, but may still be received by others nearby. In future work, this hybrid peer-to-peer / broadcast protocol could be modified to increase the bandwidth on the response side so that larger data structures could be effectively distributed throughout the whole system. We formalize the data distribution problem as the minimization of the age of information of the data that every robot has about every other robot in the team. The age of information is the average latency of the data obtained by each agent. Our goal is to obtain a closed-loop communication policy that each agent uses to decide its next recipient. Each robot also has the choice to not communicate to reduce the interference for others. A robot's communication policy is a function of its current knowledge of the state of the other robots and the network. The wireless channel model assumes constant power transmissions. An agent experiences a packet drop if the signal to interference plus noise ratio is below a given threshold. This model is significantly more realistic than the disk model we talked about for the flocking project, but it fails to consider any effects that depend on the surroundings of the robots, such as multipath interference. The key novelty in our approach is that each robot not only tracks the last known state of every team member, but it also maintains a representation of the flow of information through the network. On the left, we have an example in which 5 agents perform 4 rounds of communication. After these 4 rounds, we can inspect the information that Agent 0 now has access to. So Agent 0 directly obtained information from Agents 1 and 3 at time steps 2 and 4 respectively. But the states of Agents 2 and 4 were provided to Agent 0 by Agent number 3. And Agent 0 records Agent 3 as the parent node for Agents 2 and 4. The resulting data structure is a tree in which a node itself is the parent, and the edges in the tree represent successful communication links to others. Agent 0 can now make more informed decisions about who to communicate with next, depending on the location of the other robots, and also the last known successful route to every other robot. Now, our goal is to formulate the data distribution problem as a reinforcement learning problem. The observation space for each robot is its local data structure with the last known states of the other team members, in addition to the last known connectivity of the team. During centralized training, if we're looking at all of the information from all n robots, we have n different graphs with n robots each, resulting in n squared total nodes. The action space of each agent is n discrete options, transmitting to one other team member or not transmitting at all. The reward is the negative of the age of information averaged over all of the agents in all time steps. The reward is centralized for the entire team, and we use centralized training since this task is fully cooperative. We use the proximal policy optimization algorithm to train a value function and policy by centralizing all of the observations from all agents along with the reward signal. But the structure of the policy ensures that each agent's actions depend only on its local data structure. So at inference time, the policies can be executed in a fully distributed way. We parameterize the policy and value functions as separate aggregation GNNs implemented using DeepMind's GraphNets framework. The value function outputs one scalar per node, and then we sum the results to obtain one value estimate for the given state of all agents. The policy model outputs one probability per node in each agent's graph, or n probabilities per agent. To benchmark the performance of our approach, we measure the average age of information across the team. We compare the GNN performance to 3 baselines. First, in the round-robin baseline, one agent at a time is allowed to transmit, and all agents have a scheduled turn. This controller minimizes interference. In random flooding, each agent transmits to a random other agent with a given probability. This controller often suffers from interference among agents, but we tune the probability of transmission to optimize performance. The minimum spanning tree controller uses the agent's current positions to generate a minimum spanning tree in the team, and each agent then transmits to its parent in the tree. This controller can reduce interference and encourages spatial reuse. As we increase the receptive field of the architecture from 1 to 2, the GNN begins to outperform all baselines. The GNN with a receptive field of 0 could be compared to a deep set architecture that neglects the topology of the network entirely. This result shows us that tracking the topology of the network and using it in making communication decisions is extremely important. The difference in performance between the baselines and the GNN narrows for a team of mobile agents, as a controller must balance exploiting the known topology versus discovering better routes as agents move. In this figure, we compare the performance of two sets of GNN controllers. The orange curve is the performance of the controllers trained on each team size, and the blue curve demonstrates the generalization across team sizes. The GNN generalizes very well from training on 40 agents to a team of 80, but beyond 80, training was limited by GPU memory because the memory complexity of centralized training scales with the number of agents squared. In the previous experiments, we were isolating the data distribution problem. Now, let's see if we can actually use the distributed data to make controlled decisions. As an example of an application, we decided to revisit flocking. For this experiment, we're actually using a simplified flocking controller that ignores spacing between agents and just seeks to align velocities. Each agent decides their acceleration based on average velocities of everyone in their buffer. Flocking relies on up-to-date information about teammates' velocities. So now that we have a particular task, there's an interesting question. What should we use as the reward function for reinforcement learning in this task? On one hand, we can quantify the flocking performance via variance and velocities. But on the other hand, we already saw that the age of information serves as a great reward function in previous experiments. So for this experiment, we varied the initial agent velocities and trained two sets of GNN controllers. One GNN was trained using the variance and velocities as the reward, pictured in red. And the other GNN was trained using age of information as the reward, in orange. What we see in practice is that training with the age of information is more stable and effective than training with the variance and velocities. It results in lower age of information and also lower variance and velocities. This could be because the variance is a less direct signal for communication decisions. Unfortunately, as velocities increase, our GNNs are outperformed by the baselines. The task of flocking is particularly sensitive to the decisions at the beginning of the episode, and our controller starts out with zero information about team members. In future work, we could design a protocol that allows agents to optionally request responses. Our protocol's two-way communication requirement ends up wasting time when requests fail. Ultimately, there may also be more compelling use cases than flocking for this data distribution approach. Now, let's visualize the operation of the GNN communication policy. On the left, the links pictured in black are successful, and the red links indicate interference. The agents that eavesdrop successfully are pictured in light blue. On the right is a visualization of the connectivity of the network from the perspective of agent 0 marked in green. The GNN allows agents to use both the delayed information about others and information about the topology. In mobile teams, the network topology must change as agents move. It's interesting to see how some of the connectivity information gets stale when agents move further from each other, and then suddenly a better route is found to connect the team. Our protocol could be applied to any task reliant on low latency information distribution within a robot team. Today, I've covered several core problems in large-scale multi-robot systems: coordination, control, and communication. We captured the structure of these tasks using graph abstractions, which allowed us to train scalable graph neural networks. The ability to train these architectures in a centralized way is also essential to the scalability of these approaches to teams of up to 100 agents. But despite these advances, there are still lots of research problems in the field of embodied multi-agent systems. First, we anticipate several challenges in implementing this work in hardware. The problem of transfer learning from simulation to hardware will require a hierarchy of controllers. The high-level coordination policy could possibly be transferred zero-shot to real systems, but the lower-level controllers may need to be fine-tuned on the robot. The extension of this approach to heterogeneous teams is another interesting direction. Moreover, the team could also include human team members, requiring the design of human-robot interfaces. The use of this approach in adversarial or non-competitive scenarios may require resilience within the team, in which robots need to react to loss of team members. But in most situations that are not purely cooperative or adversarial, autonomous driving is an example of a task in which agents may have competing objectives, but must cooperate for safety. And GNNs are already in use for behavior prediction of human drivers. I'm grateful for the support of my advisors, Alejandro and Vijay. I'd also like to thank the committee for their help in shaping this thesis and the collaborators I've been lucky to work with.